We decided to take the results of this test and try to apply it to something real. Okay, so first off, I'm taking off my eBay hat. All right, I am Data Center Pulse, period. We went off and did an independent test with data with generic internet-based load and ran some of these configurations. Okay, so James Monahan, you stand up for a second? So James Monahan is, I don't know what your title is, but he works at California Data Center Design Group. And it pulled him back in to run these tests. And where we started was on the absolute right side of that chart. We wanted to go do our test starting at 85-degree inlet. So let's go there. We're doing a pre-test for the Chill-Off 3. We took one server, 1U, 2-node, 1,000-watt power supply, 4 130-watt Westmere 6-core processors from Intel. So Supermicro and Intel and Coolidge, thank you very much for jumping in and doing a rapid test to see what happens here. But we took this 1U server primarily because we wanted to see what would happen with really heavy wattage CPUs with very high temperatures. And these are the objectives we went after. The repercussions of hot temperatures in your data centers on the performance of your compute. In other words, 85-degree inlet air. Remember, ASHRAE's upper limit is 80.1, correct? 80.6? All right, sorry. Room full of engineers. So point being, we're above that number. All right? Recommended number, right. So that band, we wanted to go above that. The second part was, is there really a difference between air and liquid cooling when it comes to the performance on the server? The third one is overclocking and underclocking. What we're looking at in the Chill-Off 2 is the efficiency of the cooling system. We're not looking at the efficiency of the productive work that's done by the IT. Okay? So we stepped back and said, great, we got all these cool things that we can do inside of the data center, but they can be counterproductive to the IT group. So let's look at the whole picture. Let's look at some results. I'm doing this quickly. Running the data center at 85 Fahrenheit in this test, and we can share some information on this. I'm not going to go into all the details of it, but the bottom line is that there was no impact to the compute performance at running 85-degree inlet, both liquid and air. The difference is that there was a 4 to 7% increase in leakage current. Okay, so leakage on the actual system. Just for those that may not know what that is, we measured the actual power supply, we ran our tests, and we saw that when we were up at the higher frequencies and the higher voltages, we saw more draw, but we saw the same amount of load, the same amount of compute performance. Literally, the heat on the system was causing more watts to be consumed for that work, between 4 and 7%, based on the workload. Okay? Next one, air versus liquid. The difference we saw in this, because we took a Supermicro server with their fans, ran this thing at these temperatures, then we took them off and put on the clustered systems plates, the heat sinks and the plates, put it into a Coolidge rack, and which I dubbed the bit fridge, by the way, that rack, and actually ran the same test. The refrigerant was running at 95 Fahrenheit because the refrigerant to the water had to be 85 outside to make sure it was apples to apples. Okay? But what we saw is 6% decrease in the actual power due to the removal of server fans. Okay, so it's directly attributable to the fans that are in the server. And the shadowing effect was really big. To explain shadowing, so you've got a CPU, behind it you have memory. On the other side you have memory and a CPU. Okay, so we had 1U with 2 nodes, and we had 4 of those processors. And what we saw is there was a 7 to 13 degrees C rise in temperature in air across those devices. So when we went from the CPU, it heated up the air and heated up the memory up to 13 degrees C behind it. So that shadowing effect is a big deal. Okay, that's probably causing the leakage and other things that are happening in the server. But the biggest thing for me in this is that by running this test, we found out something new. We said, let's overclock all these and see what happens. If you guys know me, I'm trying to go back and see how much performance I can get out of the system. And I think we really need to push the chips. We found underclocking and overclocking together did some pretty incredible things. So 18.2% savings in overall wattage of the system if we match the CPU frequency with the workload dynamically. Let me step through that in just a sec here. This chart, notice up on the top, 3.3 gigahertz Westmere chip, again, 130-watt CPU. That line on the top If you don't change the frequency, everything below it, you're going to consume. Okay? You're just running the CPU with this. It's like kind of staying at 100 miles an hour in your car all the time. We decided, back off and speed up when you need to. Look at the workload, the green. That is just transactions per watt, consider it. So we started out low, and then there's other traffic coming up, and then all of a sudden we got a peak. So we decided, when we've got that workload, start at the beginning. We lower the CPU frequency to 2 gigahertz because the amount of transactions we need to do matched to that frequency. Then it went down, and we stepped down again. And it started going up. We kept stepping up the frequency. And the delta, all the differences between that, the wasted cycles and watts, when you take that over a 24-hour period, just matching the CPU performance with the actual load was 18.2% reduction in the overall consumption of your server. Duh. Why the hell aren't we doing this stuff? Okay, so this is one server tested in one configuration, okay, with some workload. Now, there are ways to do this. The only way we could do that, and James had a hell of a time trying to figure this out, was to get into the CPU and really see what the proc hot and Pecky temperature and all these other things Henry would understand and I don't. So all of those things, we had to get in there to see the temperatures. We also had to get in there with the hooks to be able to adjust the frequency of the CPU. Okay, but guess what? Intel already has all the hooks in there to adjust the frequency of the CPU. Duh. So why don't we take advantage of that? There are many manufacturers looking at doing this from power management, but this is really performance management. Okay? So I just wanted to share this information because now you look at what happened in the chill-off 2. It's significant to understand, you see what happens with the temperatures as we go back up. I want free cooling year-round in the data center locations I have, including Phoenix, Arizona. I can get it. We just proved it can happen. Because the temperature outside can be 130 degrees. With the humidity, it's 85 max 2 days a year. So with that, Mark didn't get that, so let me explain. So with the, no, okay. So let me clarify that again, okay? The outside temperature, it's very dry in Phoenix. And Mark can probably do this a lot better than I can. But the point is, the real temperature I need to cool is 85 degrees Fahrenheit. Max, that's the top peak of the temperature with the humidity mixture, correct? Okay. It's all about wet bulb, and I'm not a mechanical engineer, okay? But guess what? We got results here. Can we get the mic over to James so he can explain that a little more? And yes, Mark, you've reached your limit of questions as well. No,
no, all that is just it's a 78-degree wet bulb burst in Phoenix, and then with a 7-degree approach onto the towers. So that's what we were looking at. If you can actually eliminate the chiller and just run that tower water straight to some form of a refrigerant to water heat exchanger. And so that's where we got the number, and that's when we did the air testing. We kind of went above the ash rate because we were trying to do the comparison of apples to apples.
So any questions? And Mike and others, feel free to jump in here.
Dean, are there software already available to optimize that?
There is software available to do that. I mean, if you look, I think it's Modius and a number of other companies have the ability to lock into it. HP has got a thing, I forgot the name of their package.
Tivoli, yeah.
Not Tivoli, but there's a certain,
Okay.
Well, anyways, yes, there is, right? And there's Node Manager from Intel.
Okay.
And the Node Manager is the thing that gives you the hooks back in to control that system. Right? But some things are proprietary, some aren't. Yeah. The point is, we were able to go figure out how to get into it. Yeah. And there's no reason why you can't go back and have your application tell the frequency of, or the CPU what frequency it should be running at. Now, remember, there's no one size that fits all here either, because workload that's on here is an internet-based type transactional workload. There's others that wouldn't work that way. But what we did see is, if you take a virtual machine type configuration versus this thing, they're relatively close, depending on utilization. Ray?
So during the IT part of the adaptation thing, they brought a bunch of the IT vendors in to talk about onboard power management, a lot of the tools that are there. Of course, as you know, there's a whole bunch of different ones.
Go ahead and repeat that, Ray.
Yeah, obviously, got all the IT manufacturers to participate in our ad hoc IT committee to talk about just this topic. And they shared with us all the data on all their different machines and classes of machines and the different types of onboard power management, a lot of which exist because they're inherent in either the Intel chipset or they've built them into their own BIOS. Okay, so there's different levels. They do different things. They all have different performance impacts. But that net savings is real. And their data they shared with us showed it ranged anywhere from 7.5 to roughly 20%, which is what you're seeing. And that's one of the things that in the IT efficiency piece of LEAD, that's one of the things that we're going to encourage is if you enable these onboard power management or your higher level power management solutions, you can get credit for this because it's real savings.
Yeah, and just to clarify, there's power management and there's performance mapping. This is very different, right? Because we're basically telling the CPU to lower its voltage and lower its frequency so we can now get the performance we need, but we don't have as much wattage. But power management is turn off cores, turn off different things that you can do that. Both of them do, save money.
Yeah, but you can also clock down the CPUs and they have BIOS that does that as well as
sure.
one of the options. And that's the piece I was talking about. It's exactly what you were talking about.
Yeah.
And that's the key is why run higher clock cycles or when the units are idle, why are you letting them run it with the gas pedal all the way down to the floor?
Boom. Autobahn.
Question? Was there a sweet spot in terms of the temperature? Was there a sweet spot in terms of the server inlet air temp where you before you started having that leakage?
James, you want to jump on that?
Yeah, so we actually did a lot of, playing with the server fans to eliminate it, because in certain instances we would have run the CPU hotter, but then we'd notch up the server fans just to see what would happen, and you would see the leakage current decrease because we had all the server fans, so you could extrapolate it out. I would say, to be honest, about 75, 76 degrees Fahrenheit was where we were kind of I was finding testing, just playing, that was kind of the happy medium of where we got,
Hey, let me throw two more points in here. So the first one is that the chip itself, we're measuring all the way back in proc hot. Okay, so we're seeing inside the chip. And there's this threshold that where the CPU itself, if it gets to here, it will throttle itself. It will actually slow down and go into states where it won't let it burn itself out. Okay, so that's between 40 and 80 C. What we saw is when we went to 100%, we were still 20 C away from that thing even touching its throttling, even at 85-degree inlet. The other part here is 85-degree inlet is just a small period of the year. So you're just covering for this little peak. The other part is this isn't real workload. There's more opportunity. This is saying that your systems are going to go to 100%. Most data centers don't let their systems go to 100%. Disaster recovery, balancing, etc. You run those lower. So all that stuff above where your main load is gravy. In other words, we've got 18.2% here, assuming that we go from 20 to 15% to 100% workload. If now we're going between 15 and 50% workload, everything above that is a savings.
Any more final questions?
All right, then.
Any last minute questions for Henry?
He's done.
1 minute early to go to beer.
He's done.
Thanks, everyone.
Thank you.